Hello everyone. I'm going to do a quick little lesson on two-sample inference procedures with means. So this is a follow-up. This is the follow-up from the matched pair. So now we're moving from a one-sample into a true two-sample inference procedure. So we're going to talk about both confidence intervals and hypothesis tests using two samples. So to start us off, the goal of these inference procedures is to compare the responses to two treatments or to compare the characteristics of two populations. So this is the first time we've been talking about two separate treatments or two separate populations and comparing them to each other. And in order to do that, we need to use these two sample procedures as opposed to the one sample that we've been doing. It does require that we have independent samples from each treatment or a population. Up until now, with matched pairs, we've been doing dependent samples. Now we're talking about independent samples, which require something different to do. Remember back from when we studied this in Chapter 7 that if you have a combined mean, if you're doing the two random variables x and y and you're combining their means together, that this was the formula for the combined mean, and this is the formula for the combined standard deviation. So hopefully you remember that from Chapter 7. If you're not, you should write it down because this is what we're going to be using a lot for these procedures. We're going to be interested in the difference of means. When we're comparing two samples together, we are predominantly going to be talking about the difference in means. So we're going to use this standard deviation to help us find the standard error. So here's a situation that should seem familiar. We have a population of adult men that have a mean height of 71 inches and a standard deviation of 2.6. We have a population of adult women with a mean height of 65 and a standard deviation of 2.3. We know that heights are normally distributed. Describe the distribution of the difference in the heights between males and females. That wording should seem familiar. We're talking about describing distributions. We're talking about what's the center, is there anything unusual, is there any spread, or what's the shape going on here. So in this case, this is a normal distribution because it said both the men's heights and the women's heights were both normal. Therefore, the combined distribution would be normal. We would subtract to find the mean, so 71 minus 65 would give you a mean of 6 inches. And we would use the square formula to find the standard deviation. So 2.6 squared plus 2.3 squared, take the square root of that, and we get the 3.471. So that's how we find the standard deviation of the differences in the heights. So here's what we have. We have the female distribution, we have the male distribution, and we're going to combine them together to find the difference, male minus female, and it's going to wind up looking like this, with a mean of 6 and a standard deviation of 3.471. And this is the difference when you subtract the two, the male minus the female, to get the distribution of the differences. So then we can ask some follow-up questions. First, what's the probability that the height of a randomly selected man is at most 5 inches taller than the height of a randomly selected woman? So what's the probability the difference is greater than 5? So to do that, we would do this statement. It's a normal CDF. The probability that male minus female, the difference is at most 5, so less than 5. You'd have a lower bound of negative infinity, an upper bound of 5 with a mean of 6 and a standard deviation of 3.471. What's the 70th percentile for the difference in heights of a randomly selected man and woman? When you're being asked a question about 70th percentiles, then we're doing an inverse norm. So we would use inverse norm to help us figure that out. So the area is 0.7, again a mean of 6 and a standard deviation of 3.471, and we would get a 7.82 difference for the 70th percentile. Now let's talk about a sample. Let's say instead of a single man and a single woman, we're talking about a sample of 30 men. And so what's the probability that the mean height of 30 men is at most 5 inches taller than the mean height of 30 women? So what's going to change is the standard deviation has now changed. Instead of the 3.471 that we had before, our standard deviation now is 3.471 divided by the square root of 30. And so we would use that then for our standard deviation. We would still use the same inverse norm procedure that we used on the last slide. The only thing that's changed is the standard deviation has changed, and it gives us a lower percentage. 70th percentile, same exact idea. We're going to do an inverse norm of 70%, so 0.7 with a mean of 6 and a standard deviation of the 3.471 divided by the square root of 30, and we get 6.332 inches. So it dropped a little because we're talking about a sample as opposed to individuals. These problems should seem very familiar because we've done them before. These are all from Chapter 9. It's just now we're talking about the difference between two things. Okay, so for a two-sample procedure, here's the assumptions that we have to use. We have to take care of. First, instead of a single SRS, we have to have two SRSs, or two randomly assigned treatment groups. So that makes sense. We're doing a two-sample. We should have two of them. The samples must be independent. That is key. If they are not independent, then this is a matched pairs problem. If they are independent, it's a two-sample problem. Both distributions are approximately normal. And we can establish that in a variety of ways by looking at the box plot, by looking at the sample size. They could be normal to start with, in which case that takes care of that. So large sample sizes, you should always graph, if you're given data, you should always graph both sets of data to see if they are both appear to be symmetric with no outliers. And then finally, sigmas can either be known or unknown. If the sigmas are known, we're going to do a z-test. If the sigmas are unknown, we're going to do a t-test. Here's the formulas. Now, in real life, as we've talked about in class, we will hardly ever know both sigmas. So almost always this will be a t procedure test. As far as degrees of freedom, we have two options. The first option is we simply use the smaller of the two values, either sample size 1 minus 1 or sample size 2 minus 1. So we're going to be conservative. It will produce conservative results. It gives you higher p-values, lower confidence, but better safe than sorry. So option 1, if you have a sample of size 15 and a sample of size 30, we're always going to use the smaller of the two of them. The second option is to use an approximation used by technology. So get a load of this formula. This is the formula that the calculator uses to calculate your degrees of freedoms for two samples. Lucky for you, you do not have to memorize it because the calculator does it all for you. But that's what the calculator does when it calculates the degree of freedom. So when in doubt, use the calculator because it's doing all the work for you and it's going to give you a more accurate estimation. But if you have to, you can always just go with the conservative estimate up top, which is to use the smaller of the two sample sizes. Confidence intervals. Here's your formula for confidence intervals. The statistic will be the difference in the two x-bars plus or minus the critical value, which is that exact same t star that we've been doing all along, times the standard deviation of the statistic. And here's the new formula. So we take the two separate standard deviations, and you divide by so it's s divided by the square root of n, s2 divided by the square root of n, and then you square both of them and you take the square root. Okay. And then remember that the part underneath the radical sign is called standard error. For a hypothesis test, the test statistic is t, and it's going to be the difference in the means, x1 minus x2, minus the difference in the population means, divided by that same standard error that we just wrote down previously. Most of the time, the difference in the means will be 0, so most of the time that part will be 0. Now your calculator will ask you a funny question when you go through and you do this, and we'll see that in a little bit. It'll ask you if you want to pool your data. Pooled procedures are something that is used when you have two populations that have the exact same variance. If they have the exact same variance, you can pool the data and get something that's a little bit more precise. When you do pool, you average the two sample variances to estimate the common population, but we're not going to use any pooling on the AP exam because we will never know the variances of the population. So if we don't know if they're the same, we can't pool. Since we don't know, we just have to tell the calculator no. So always, always tell the calculator no for pooling. Alright, so here's an example problem. Two competing headache remedies claim to give fast-acting relief. An experiment was performed to compare the mean lengths of time required for bodily absorption of brand A and brand B. Absorption time is normally distributed. 12 people are randomly selected and are given an oral dosage of brand A. Another 12 are randomly selected and given brand B. And then here are the results. Describe the shape and standard error for the sampling distribution. Well, if we're looking at the differences in the mean, then we would say that we would subtract them. It's a normal distribution because both A and B were normal. The mean would be 20.1 minus 18.9. The standard error would be 8.7 squared divided by 12 plus 7.5 squared divided by 12. Add those together and then take the square root, and that gives us a standard error of 3.316. Then we can jump into finding a 95% confidence interval difference. So here's how that's going to be set up. First, we state our assumptions. We have two independent, randomly assigned treatments. We are given that the absorption rate is normally distributed, so therefore we know we're dealing with a normal distribution. The sigmas are unknown. Formula and calculations. This is a t-interval, so we're going to do this formula that you saw previously with a degree of freedom of 11. Plug in your x-bars, look up your t-star value on the frequency chart, plug in your standard error, which is this part here that my arrow is going around, and then let your calculator do its magic, and there is your interval. We use a t-star for a degree of freedom of 11 and a 95% confidence level, just looking in the pink book or in the back of your textbook. Right? Always remember to think Price is Right. It's the closest without going over. We can't go over 12, can't go over 11, so we have to use the closest one. And then conclusion and context. We are 95% confident that the true difference in mean lengths of time required for bodily absorption of each brand is between, and there's our numbers. Make sure you highlight those words in red. Anytime we're doing a two-sample t-test, we are talking about a difference in means. So we have mean 1, we have mean 2, and we're talking about the difference between them. So you always want to use that terminology when we're talking about two-sample tests. So make a note of that. When we talked about matched pairs, we were talking about the mean difference. What's the average difference between the pre and the post-test? When we're talking about a two-sample, we're talking about a difference of means. So you should write that down because that's going to come back again. We're going to be talking about that a lot in class. And people always get confused with the difference. So put a little star next to that. Alright, so here's an example problem that I want you to do on your own. And then when you come into class tomorrow or the next day, we will discuss. Alright, so you might want to press pause for a minute and write this out and then see what you can do. And when you're ready, press play and you can go on to the next slide. Alright, welcome back. So now we're going into our hypothesis statements. The null is that the true difference in means is 0, that there is no difference in means. So you would do mean 1 minus mean 2 equals 0. Or you could say there is no difference and that they are equal. That would be another option. The alternate, there's a couple of different ways you could write that. u1 minus mu2 is less than 0, or simply mu1 is less than mu2. Or you could flip it around and do mu1 minus mu2 is greater than 0, in which case you could write mu1 is greater than mu2. Or you could write mu1 minus mu2 is not equal to 0, which means mu1 does not equal mu2. So any of those versions are acceptable. Be sure to define both mu1 and mu2. You need to tell me what they are. A lot of people are still having issues and they're not writing out their definitions for their mu's, and you need to make sure this time you're doing both. For a hypothesis test, remember here was the formula that I showed you earlier. All right, so it's the same formula that you should have written down already. Since we usually assume that the null is true, this equals 0, so we can usually leave it out. All right, so usually it's just written out without that, because usually we assume that there is no difference in means. So back to our brand of, I don't know, whatever medication this was, and here's the data that we had from earlier, and we want to know this time, is there sufficient evidence that these drugs differ in the speed at which they enter the bloodstream? So let's state our assumptions. We have two independent randomly assigned treatments. We know that the absorption rate is normally distributed, and we know the sigmas are unknown. Let's write our hypothesis. Our hypothesis is that there is no difference. Mean A equals mean B. The alternate would be that there is a difference. Mean A does not equal mean B. we're going to spell out what that means, where mu of A is the true mean absorption time for brand A, mu of B is the true mean absorption time for brand B. Be very specific. Formula and calculations. So here's our formula. Plug in all the appropriate numbers and we get a t statistic of 0.361. You can use TCDF just like we did previously. Now that you have your t statistic, we're using the exact same procedures that we used before, and we get a p-value of 0.721. Now the degree of freedom. This degree of freedom that's listed here is what the calculator calculates when you do on your calculator, if you go into the stat menu, we do a 2-sample t-test. Right? That's what you're looking for when you go into your stat menu, is a 2-sample t-test, because and if you do that, it will give you your degree of freedom. It will do that calculation for you using that great big formula that I showed you. So it's a 2-sample t-test, and it'll give you the degree of freedom that you can then write down. Finally, conclusion. Since the p-value is greater than A, I failed to reject the null. There is not sufficient evidence to suggest that these drugs differ. All right, suppose the sample mean of brand B is 16.5. Does that change things? Does that make brand B faster? So we would do a new test statistic and change it to 16.5. We get a new t-value, and we get a different p-value, but the p-value is still pretty big. So no, it doesn't change anything at all. All right, here's an example that I would like for you to do. So again, this is in your note packet. Press pause, see if you can figure out how to do this, and then we'll talk about it tomorrow when you're ready. Press play, and we'll finish this up. We're almost done. Welcome back. All right, so last little thing I'm going to talk about, robustness. When we talk about robustness, we say 2-sample procedures are more robust than 1-sample procedures. It is best to have equal sample sizes, but not necessary. So if you have 2 that are equal sample, that's the best thing, but it's not always 100% necessary. And now remember what I mean when I say robust. An inference procedure is called robust if the probability calculations involved in that procedure are fairly accurate, even when a condition for using the procedure is violated. So even if one of the conditions, say the normality condition, is violated, it still gives you good, accurate p-values. That means that procedure is called a robust procedure. 2 samples are more robust than 1 samples. So that's a good thing to know. And then the last example I'm going to give you. So a modification has been made to the process for producing a certain type of time-zero film. Because the modification involves extra costs, it will be incorporated only if the sample data indicate that the modification decreases the true average development time by more than 1 second. Should the company incorporate the modification? And here's our data. So the company wants to know if there's a difference of more than 1 second. And if there is, it'll spend the money to modify this, and if not, it won't. So in this case, our null is going to be that the original minus the new equals 1. The alternate is that the original minus the new is greater than 1. Right? We have the same assumptions that we've had all along. 2 independent SRSs, they're approximately normal due to the box plots. There's your box plots. You can see that they're normal. And the sigmas are unknown. Remember to tell me what mu is. Mu sub 0 is the true mean developing time for the original film. Mu sub m is the true mean developing time for the modified film. And then we throw in our formulas. Right, so this is the formula that you've written down a couple of times now. Notice that mean 1 minus mean 2. We want to know, is it 1? Is the difference more than 1? So that's where the 1 came from. And we get a t-value of 0, which means we get a p-value of 0.5. So we would fail to reject. There is not sufficient evidence to suggest the company should do this. Okay, so that's a real quick version of 2-sample t procedures. And of course, we will be talking about this in class and doing lots more examples over the next week or so before spring break. So have a good evening, and I will see you tomorrow.